Welcome to Homework Lib.
So in this question is actually follow-up on example 42.2, example 42.2 of this book. So in this question, we have the rotational energy level of carbon monoxide, and this is already calculated. And then this question asks if the energy of the rotational molecule can be expressed by this expression. This is like the classical expression of rotational energy. And then it's asking if for the L equals 1 level, this is the classical rotational energy, then what is the angular speed? Angular speed of the rotational molecule, what is the linear speed of each atom, and then what is the period of it. So the first thing we do is we need to review a little bit of 42.2. From example 42.2, a couple of things we found. We found when L equals 1, the energy is 0.479 MeV, which is also roughly 7.674 times 10 to the negative 33 joule if you do the conversion. And then we also found that the moment of inertia is 1.449 times 10 to the negative 46 kilogram meter square. Okay, so this is already given from example 42.2, and in part A we're looking for the angular velocity. So in order to do that, we can right now we are saying that we are assuming this energy can be described by the classical kinetic energy, so we can just equate them. So we have K equals 1/2 I omega squared equals E1. So omega is just omega equals square root of 2 times E1 over I. And then we put in E1 and I, and we can find this to be equal to 1.3 times 10 to the 12th radian per second. So that's this. And then we can look at another part. In part B, we're looking for the linear velocity. In order to find the linear velocity, we need to we have linear velocity. We have the carbon and we have the oxygen. So V1 and V2, I'll call them V1 equals R1 omega 1 and R2 omega 2. So they have the same angular speed, but they travel at different radiuses. And then it's nice that we actually, the example 42.2 also gives us the radius of the carbon and the oxygen radius of the oxygen and the carbon atom. So we can use that. One of them is, this is oxygen is 10 to the negative 9 meter. And then for carbon, it's 0.0484 times 10 to the negative 9 meter. So this is their respective radius. And then I multiply, this one is carbon, this one is oxygen. And then I multiply them by the angular speed. So this, for carbon, we have a linear speed of 66.3 meter per second. And for oxygen, we have a speed of 49.8 meter per second. And if you think about it, it also makes sense because oxygen is heavier than carbon. So if oxygen should be closer to the center of mass than carbon is. And because of that, oxygen shouldn't be traveled as much as carbon. The radius should be smaller. And again, when I say radius, I don't mean like the radius of the atom itself. I mean like the radius they're traveling, because this is carbon, this is oxygen. And when I say radius, what I really mean is like this distance, like their distance to the center of mass in this bond. So finally, we need to look at the period. and we can find the period if we already know the angular velocity. So we'll just do 2 pi over omega to find the period is 6.10 times 10 to the negative 12 second.